Okay, I want to talk about power series in this video. So let's just go with the definition first. So let C sub n be just any sequence. I probably want to start at n equals 0 and go to infinity. Okay, so these can be positive, they can be negative, they could be complex too. We're dealing mostly with reals, but it can be any real or complex sequence. The power series centered at A with coefficients C sub n is the series, the sum from n equals 0 to infinity, C sub n, x minus a to the n, where x is a variable. Okay, so this is a series. We can think about it converging or not. Because I've got a variable in there, I need to think about it converging at each value that we would replace the variable with. The points at which it converges are called the interval of convergence, and that name sort of hints that it would be an interval, and it is. So let's see what we can say about the convergence of a power series. So our first theorem, we let the sum from n equals 0 to infinity, C sub n, x minus a to the n, be a power series. Okay, I didn't specify that it was centered at A, but because of how it's written, it's centered at A, and the coefficients are C sub n. We're going to let alpha equal the lim sup of the nth root of the absolute value of the C sub n's. Okay, lim sups always exist, so this thing always exists. And we're going to set r equal to 1 over alpha if alpha is finite. R equals infinity if alpha equals 0, and r equals 0 if alpha equals infinity. Then the series converges for any x n a minus r to a plus r. Okay. The convergence at the endpoints is unknown. So the convergence of the series for x equals a plus or minus r needs to be determined in other methods. But the series also diverges if you're not in this interval. So I'll close that interval and say it's not in the closed interval, then it's going to diverge. Convergence at the actual endpoints, we have to determine And in the last video we saw two methods that we can use to sometimes determine convergence at the endpoints. The alternating series test usually works for one of the endpoints, and the condensation test sometimes works at one of the endpoints. Okay, so let's prove this and then use it to work with some examples. Okay, so let alpha equal this lim sup of n going to infinity nth root of c sub n. The root test, let's fix some x. The root test gives convergence of the sum of c sub n x minus a to the n from n equals 0 to infinity if the lim sup of the nth root of c sub n x minus a to the n is less than 1. So let's look at this lim sup a little bit. Now, the lim sup as n goes to infinity of this thing is equal to that times that, just by some basic algebra, which is equal to the lim sup of n to infinity of, well, the nth root of x minus a to the n is x minus a, and then I've still got the nth root of c sub n. X minus a is a constant, so I can pull that out front of the lim sup, because multiplying a series by a constant just multiplies everything in there by a constant, so convergence and all that just increases by that constant multiple. Now this is the nth root of c sub n in absolute value, which is x minus a times alpha. So the series converges if x minus a times alpha is less than 1, i.e. if x minus a in absolute value is less than r, i.e. if, well, this is the distance from x to a is less than r, so if x is in a minus r to a plus r, it diverges if absolute value of x minus a is strictly bigger than r, i.e. if x is not in the closed interval from a minus r to a plus r, and convergence is undetermined by this method if x is equal to a plus or minus r. Okay, so that is exactly what the theorem had told us just by using the root test on that power series. Okay, so let's create a definition for interval of convergence. So the interval of convergence for a power series is the set of all numbers which can replace x and give convergence. Okay, so let's look at a couple examples. Find the interval of convergence for, let's do something fairly straightforward, x minus 1 to the n over 2 to the n from n equals 0 to infinity. Okay, let's do this one first. So I like to just, we proved that theorem, but the theorem says take the root test of the coefficients. Let's just take the root test on this series with x being a variable and see what has to be true about x. So I'm going to look at the lim sup of the nth root of the absolute value of x minus 1 over 2 to the n, and that's going to be equal to x minus 1 over 2 in absolute value. And this is less than 1, so we have convergence if x minus 1 over 2 in absolute value is less than 1, i.e. if x minus 1 in absolute value is less than 2, multiply both sides by 2, if x is in 1 to 3. Okay, that gives us the inside. This is the interior of the interval of convergence. We still have to test the endpoints because the root test doesn't tell us anything about the endpoints. We need to test convergence at x equals 1 and x equals 3. So let's do the test at x equals 1. What do I get for my series? I have the series 1 minus this is at negative 1. I need you guys in the desks yelling out at me that I've made mistakes. Okay, so let me draw this number line. It's centered at 1, and I have to go 2 in this direction up to 3, and I have to go 2 in this direction down to negative 1. Right? So my interval should be from negative 1 to 3. So I should have a negative 1 there, I should put a negative 1 there, I should go over 2 and raise this to the nth power, and this is from n equals 0 to infinity. Okay, so this is actually equal to the sum from n equals 0 to infinity of negative 2 over 2, so negative 1 to the n. This diverges since the terms don't decrease to 0. Okay, so we've got divergence at I missed another minus sign there. I've got divergence at x equals negative 1. Let's test at x equals 3. I've got the sum of 3 minus 1 over 2 to the n from n equals 0 to infinity. Okay, this is equal to the sum of 1 to the n from n equals 0 to infinity, which diverges for the same reason. Since the terms don't converge to 0. Okay. Let's make our conclusion. The interval of convergence for the sum of x minus 1 over 2 to the n from n equals 0 to infinity is the open interval -1 to 3. Anything inside that interval will converge by the root test. The endpoints don't converge because we tested them individually, and outside the interval they don't converge. Outside the closed part they don't converge because of the root test again. Okay, let's see another one. So that time neither of the boundary points converged. Let's track this guy. Let's check the sum from n equals 0 to infinity of, how about x to the n over n. This one will be centered at 0. It might be slightly easier to work with. Okay. So to find the interval of convergence, we use the root test. Okay, so let's take the lim sup of the nth root of x to the n over n. Well, this is equal to x in absolute value times the lim sup of the nth root of n. This is one of our common sequences. The nth root of n goes to 1, if you recall. So this is equal to the absolute value of x, which means convergence if the absolute value of x is less than 1. Okay, that gets us started. So I've got -1 to 1 is the interior of the interval of convergence. We need to test the two endpoints, so let's test x equals 1 first. If I look at x equals 1, I get the sum of 1 to the n over n from n equals, did I start at 0? I should start at 1 here because I don't want to divide by 0. So we're going to start at 1. From 1 to infinity, which diverges by, well, I've seen that twice now, Cochise condensation test. I look at the first one, and then the next 2, and the next 4, and the next 8, and that shows that I've got an unbounded sequence here. Monotonic and unbounded, it must diverge. Okay, so let's look at x equals -1. Now I've got from n equals 1 to infinity of -1 to the n over n, and this one converges by the alternating series test. Okay, so our interval of convergence is, well, -1 should be included, 1 should not be included. So that would be our interval of convergence. One of the endpoints worked, the other one didn't. Okay. So there's cases where neither one of the endpoints work. There's cases where one does and one doesn't. There's cases where both work. We have to always check those endpoints if we want to find the actual interval of convergence. And checking those endpoints, we can't use the root test or the ratio test because when those give you a value of 1, alpha equals 1 value in the root or the ratio test, you don't get any information. So I have to plug in the values and see some other method of determining convergence or not. Okay, let's do one more because I want to show you sometimes the ratio test is easier to use. So let's look at the interval of convergence for the sum of x to the n over n factorial from n equals 0 to infinity. You might recognize this as the power series for the function e to the x, or the Taylor series for the function e to the x, and this would tell us where does that Taylor series actually converge. We'll talk about Taylor series eventually. We've talked about Taylor polynomials and Taylor approximations. When something's infinitely differentiable, I can get an entire series using that method, and we can get convergence or divergence of an entire series approximating that function. Okay, so this has convergence if the lim sup of the nth root of x to the n in absolute value over n factorial is less than 1, right? So if I look at this, I get the lim sup, I get x in absolute value times the lim sup of the nth root of 1 over n factorial. And when I get to there, I'm not quite sure what to do with that. You might think, well, the nth root of n goes to 1, so I've got 1 n times, that should just be 1, but that's not true, right? N is getting bigger. When you multiply it, like we have sort of a 1 to the infinity, that's an indeterminate form, right? So we can't just say that this goes to 1. We have to do something else. So this looks more difficult. Okay, so when the root test looks difficult, we can always try the ratio test. And if the ratio test converges, the root test converges to the same thing. So let's look at the limit of the ratio test. So I've got x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. And we want to see what happens as this goes off to infinity, and that should be in absolute values. Well, I can kind of flip and multiply. This is the limit as n goes to infinity. I've multiplied by x n plus 1 times. I've divided by x n times, so I should have an x left on top. And on bottom, these guys, there's an n plus 1 times an n minus 1 all the way down. This only has an n times n minus 1 all the way down. So there's an extra factor of n plus 1 down here. And so this is equal to the absolute value of x times 0. So for any fixed x, this is less than 1, meaning the radius of convergence is infinite. And the interval of convergence is negative infinity to infinity. Okay. This one I don't have to test the endpoints because there's no endpoints to test, right? I can't just throw infinity or negative infinity in there and test them. So there's one that has a infinite interval of convergence. One more example, and then we'll end the video. So let's look at the interval of convergence of n to the n, x to the n, from n equals 0 to infinity. Okay, so the root test, I've got the lim sup of the nth root of n to the n, x to the n. This is equal to the lim sup of n x in absolute value, and that's equal to infinity if x is not equal to 0, and 0 if x equals to 0. So the only point of convergence is x equals 0. The radius of convergence is 0. So I've kind of got an empty interval, and I have to test the point that's inside that empty interval, which is at 0, and that one works out. This is kind of another case where this is when alpha equals infinity, and this was a case where alpha equaled 0. So 1 over alpha equals infinity here. That's equal to r. In this case, 1 over alpha equals 0, and that's equal to your radius of convergence in both of those cases. Okay.